Um, Hello, my name is Juhyung Lee. In this session, I'm going to talk about the effect of soil moisture on wildfires and how we can enhance the predictability of fire spreads with the remote sensing of soil moisture. Um, First, I'm going to introduce why the soil moisture is important in carbon and fire management, and what kind of technical merits we can expect from using microwave sensors. And I'm going to summarize, just very briefly summarize the baseline of retrieval algorithms for passive microwave sensors and active microwave sensors, although we briefly review how things work in the last session. This session will more focus on soil moisture retrieval algorithms. And then I will address how they are related to a fire spreads. And I'm going to wrap up this session by talking about the limitations, but opportunities we will have. Okay, so what is soil moisture? Soil moisture is by the definition that is referred to the amount of water stored in the unsaturated zone. So if you are looking at in here, this is hydrological circulations. If you see in here, uh, in here, in there's a partitioning between the water, uh, the precipitation and infiltration, and the runoff. And soil moisture is govern that partitioning. So it is one of the key geophysical variables for understanding this hydrological cycle, and also it's designated as essential climate variable of global climate observing system. Um, because I'm going to show you some more figures, but carbon uptake, the efficiency of carbon uptake, and is very important for like the prediction of flooding and crop productivity and so on. So it's very important variables in the climate. And like I said, that has an impact on the partitioning of incoming water into infiltration and runoff. If the water is too wet, then the water, incoming water, like rainfall, will gonna run off. And if it is dry, then it will gonna infiltrate into the deeper soil. And it also directly affects plant growth, like I just said. You know, it is useful information for the estimation of crop productivity. Because soil moisture is very important for soil moisture is highly related to evapotranspiration, and evapotranspiration and soil moisture, those are all important to assess how the plants then can how the water the crops and plants suck up the water and evaporate it through the leaves. Um, so, yeah, so the soil moisture is very important for the water cycle and carbon cycle. Um, and The runoff and base flow from the soil profile will determine the river flow and flooding and so on. So, which actually relates to hydrology with hydraulics as well. So as long as you can accurately estimate the soil moisture, you can predict the flooding with no actually necessarily additional model estimates. So we will going to look at relevant data in this session. And also, soil moisture is very important to understand the partitioning of water and heat fluxes because soil moisture is highly related to latent heat, and which is also related to sensible heat because to keep energy balance. So as long as we can accurately estimate the soil moisture, we can better understand the hydrological cycle and energy balance as well. And in addition, soil moisture is a residual of a water balance. So if you are able to observe soil moisture reliably with satellite, that is really helpful to calibrate and validate the model simulations, which will, if it is based upon the water balance. Yeah, so as you can see in here, yeah, this is where you will have the soil moisture will govern the partitioning between the rainfall and infiltration and runoff, and there is evapotranspiration in evaporation, which is still related to soil moisture. So this part will relate energy balance with hydrological cycle. So soil moisture is very important variable to govern on the all these circulations. But that is just general principle. In these days, because of carbon, soil moisture has become more and more important variables. So we really need highly reliable and accurate estimation of soil moisture, because when there's a shortage of soil moisture, or if soil moisture content is very low, that means the efficiency of carbon uptake is dramatically decreasing because of a low efficiency of photosynthesis. And if in the dry soils, it's highly likely that fuel moisture will also very low. Accordingly, which will enhance the risk of wildfire occurrence. So recently, the forest, which has been a huge carbon sink, has been transitioned into carbon source due to wildfires. So it's really important to monitor the capacity of carbon sequestration can be kept. So if you look at here in this figure, which shows a net biome production, which shows net land carbon uptake. So the upper figure shows direct effect of soil moisture, and the bottom one shows indirect effects of soil moisture. Indirect means that it is through temperature and vapor pressure deficiency. So when there's a variability, when there's a change in soil moisture, that dramatically change the output in net bioproduction, and this much. So That means it's very important to closely monitor soil moisture so that we can predict and manage the capability of photosynthesis. Because in this example, it says the soil moisture can change 90% of the land carbon uptake, which means that under the heat waves and when the soil moisture decrease, although planting more and more trees, that would not actually sequester carbons because decreased efficiency of photosynthesis. So this figure really suggests a lot of implications. So yes, so as you can see in here, this is relationship between soil moisture and photosynthesis in different soil layers. Uh, as the soil moisture decrease, the photosynthesis also decrease. So and here and as well. Um, this is also shows relationship between soil moisture content and photosynthesis, which is A in here. Let me pick. Yeah, here. This one. Yeah, A. This shows the photosynthesis, and B. This is stomatal conductance. Stomatal conductance is the rate at which the carbon dioxide enters the plant and water vapor exists through the stomata. So it's a key factor in global water and carbon cycle, and it is important to monitor there's a stomata closer and how things will be related to evapotranspirations. And C is transpiration rate. Um, and the D, this one is water use efficiency. Yeah. So as you can see in here, um, um, as soil moisture contents decrease, the photosynthesis also decrease, and the transpiration rate also decrease. Transpiration rate is physiological loss of water in the forms of water vapor, mainly from the stomata in leaves. And also, yeah, evapotranspiration. Yeah, so evaporation, if combining evaporation and transpiration, we sometimes call it evapotranspiration. Yeah. So, and here, like we said, yeah, stomatal conductance also decrease as the soil moisture decrease. And water efficiency. So water use efficiency is a measure of the amount of biomass produced per unit of water used by the plant. So when there's a little water used by plant, I mean water availability is very low. That means water use efficiency will go high. So it's kind of interesting relationship, and also um, it's a relationship. It is showing a relationship between plant productivity and the water use. Um, so just a take-home message is that soil moisture is important. So we can't really implement the same carbon and forest management policy under heat waves or under drought, it is important to monitor soil moisture so that we can flexibly respond to our changing environment. Otherwise, we are just adding more and more fuels to our forests. Although they will not do the job that we want, which would be carbon sequestration, right? Um, this is another study which actually looked at the NBP and GPP, net biome production, the net land carbon uptake, and gross primary products. If you look at in here on the left-hand side, you can see that control experiments versus experiments without soil moisture anomalies. So when you removed soil moisture fluctuations and impact, and you could see that global mean NBP, the land carbon uptake, pretty much stable, right? So which means that land carbon uptake is pretty much sensitive to soil moisture. If you look at the bottom, they have tested several different models. And it shows that when there's no soil moisture anomalies, standard deviation has been decreased. So showing that NBP and GPP and respiration, those things are all sensitive to the soil moisture. And this suggests there's a strong relationship between soil moisture and atmosphere, and there's very interesting feedback between the land surface and atmosphere, and which dominates and govern land carbon uptake variability. So soil moisture is very important to determine our carbon policy and to understand what's going on in forests, whether we have to plant the trees or do we have to cut and harvest the trees. Yeah, these are the same messages. As the temperature goes up to the right hand side, this direction, these directions, and if the drought continues and temperature goes up, and then air quickly become dry and hot, and this actually negatively affect the plant carbon uptake, and photosynthesis becomes ineffective. So we made lots of attempts and efforts to reliably observe soil moisture, and these are some examples. What kind of sensors can be applied to retrieve soil moisture from the sensors? Top 2 is the most common one and has been designed to detect soil moisture for the first time ever in human history. They operate at L-band, and SMAP actually suggests and produce high resolution and high accuracy, highly accurate soil moisture. However, it's highly influenced by the surface roughness and vegetation canopy structure and water content. And then SMOS, which is a multi-angular acquisition capability with a low sensitivity to cloud and vegetation contamination, and high sensitivity to soil moisture fluctuations. And poor spatial resolutions and highly influenced by surface roughness and vegetation cover. However, SMAP and SMOS has the use the same type of L-band radiometers, and although SMAP is uh, combined with some high resolution active sensors, still they are also vulnerable to vegetation errors and some vulnerable or uncertainty in the estimating vegetation water contents and vegetation optical density. So it's really yeah, depends on the cases and the reasons of your interest. Um, Also, there was MSRE, which has been applied to estimate soil moisture years ago. They have long-term observations and high revisit frequency. However, the spatial resolution was lower than SMAP or SMOS data, and uh, because they C and X bands, so their penetration depth, wavelengths is much shorter than the L band of SMAP and SMOS sensors. So which means that it's highly likely that their microwave will be scattered on the surface of leaves, rather than, entering trunk and penetrating through trunk and branches. And Sentinel-1, yeah, it's very high resolution and high temporal, yeah, resolution data you can get. However, it's highly related, highly influenced and contaminated by surface roughness and vegetation conditions, which means Sentinel-1 is also Sentinel-1 also operates at C-band, so the wavelength is shorter and penetration depth is shorter. So usually largely scattered on the surface of vegetation rather than entering the vegetation layers. So when the pixel is bright, we don't really know whether that is because of roughness or vegetation structure or the soil moisture. So we will going to talk about this in more detail later on in this session. And for the rest, like Landsat and MODIS, they are they use something like infrared sensors. So accordingly, their spatial resolution is very high and multiple bands, and yeah, spectral is available and usually applied for the estimation of vegetation property. Yeah, and also they are restricted by the atmospheric conditions because of cloud interference and some night effect. You can't see anything in the nighttime and so on. So those are some difference from the microwave sensors that we just talked, like SMAP and SMOS. However, all these sensors can be applied to estimate soil moisture. And in addition to these, there were actually more diverse sensors available for soil moisture, like a scatterometers, like ASCET or ERS1 has been applied to estimate soil moisture, and ASAR, yeah, and radar set has been applied to estimate soil moisture. Um, what else? Um, there's AMSR2. Yeah, it's kind of follow-up as a sensor. Um, what else? What else? Yeah, actually there are many applications. Mm, ASCET, Sketterometer, ERS. Mm, yeah. So for your convenience, when we estimate soil moisture, from microwave sensors because of all those limitations and disadvantages of traditional sensors that we just discussed in previous slides. It's the reason to target in the electromagnetic spectrum is just right here. Yeah, it's longer than infrared wavelengths. However, there's an atmospheric window, so we can't really use all the area. We should really consider atmospheric opacity. We are able to detect soil moisture through dielectric constant because of their close relationship. If you look at the figure on the right hand side, dielectric constant has positive relationship with soil moisture contents. However, they are sensitive to frequency, what kind of frequency you use, your sensor use. They have a little bit a different relationship, but all of them are positively related. And if you look at the left hand side, there's a dipole moment of the water molecules, so which causes orientational polarizations, so which would make high dielectric constants, and which means high soil moisture is high. So this is how we can interpret and our data to read and monitor soil moisture. Like I just explained, if using the microwave sensors, these are, there's almost no interference in atmospheric layers. Microwaves usually penetrate through the clouds, dust, smoke and snow, and light, less intense rainfall. So we can say that it is weather independent. Also, we can detect the parameters of our interest even in the nighttime. These are just the figures that in recent years, around in here, around here, recently several microwave sensors has been launched, and more data will be available for us, like X-band, C-band, Ku band, and L bands. And L bands are in blue here. This and this map and smooth and Aquarius and so on. However, in addition to L band, there are more diverse options for C band and X band and Ku bands, which are a little bit shorter than the L bands. However, more and more microwave sensors has been launched so that they are ready to be used. So yeah, it would be interesting to explore excuse me, explore those new sensors. Yep. So when there's a wildfire, actually there's a the fuels to be burned are actually widely distributed, even in the floor, on the trunk, and on the crown. So it would be more advantageous for us to target all of those rather than just focusing on just leaves, like LAI or a vegetation index. So there's a technical merit if using the L-band microwave sensors. It's better penetrate through the vegetation layer. Yeah, as you can see in here on the right hand side here, at and L band here, 1.4 gigahertz, has a higher transmissivity as compared to this X band. So vegetation transmissivity to soil emission is very effective when using L band frequency, which is much higher than the C band or X band. So obviously there's a technical merit if using the L band. I think we have explained about these figures on the left hand side before. And so at the L band planks, Rayleigh and Jeans approximations is really works fine and holds well, and Brunei's temperature and radiances are directly proportional.